Okay, this video is on Chapter 2, Section 6, and the topic is graphs of rational functions. What you'll learn about are rational functions, transformations of the reciprocal function, limits and asymptotes, and analyzing graphs of rational functions. And why we're learning this, rational functions are used in calculus and in scientific applications such as inverse proportions. Let f and g be polynomial functions with g of x not equal to 0. Then the function given by r of x equals f of x over g of x is a rational function. Find the domain of f and use limits to describe the behavior at value or values of x not in its domain. So our function f is 2 over x plus 2. And remember, the domain of a function is where is it defined? That's what you have to ask yourself. And so determining where a function is defined is really a question of where is it undefined? We find those values that make the function undefined, pull those out of the set of all real numbers, and then whatever's left is usually the domain of our function. So to find the domain of f, the domain of f is all real numbers except x equals -2, because the denominator of f is x plus 2. Where is x plus 2 equal to 0? Well, the answer is at -2. So that's where the function f is undefined. So we remove that number from the set of all real numbers, and whatever's left is the domain of f. So here we have a graph of our function f, and we see here at x equals -2, here's -2, we have a vertical asymptote. Okay, so we have a vertical asymptote. Our graph is nowhere on that vertical line, but there is a graph everywhere else, all other x values. Okay, so how we would write that domain, we would write the domain of f as -infinity to -2, and then u for union, -2 to infinity. All right, the u means this set and this set, this interval and this interval put together is the whole domain for this function f. Now, another thing that we're going to talk about is another way that we can represent this is in limits, in terms of limits. So here are this first limit, the limit as x approaches -2, and this little plus sign means as x approaches -2 from the right, what is the limit of f? Meaning, what does the function do as we approach -2 from the right? So this is asking us, what's the graph of f doing as we approach -2 from the right? So again, here's -2. So as we approach -2 from this direction, what is the graph of f doing? Well, if we travel and trace along f, as we approach -2 from the right, the graph is going up. And it's going to continue going up as we get closer and closer to -2 from the right. That graph is going to continue to go up, and it's going to increase without bound. So how do we represent that? We represent that with an infinity. So the limit of f as x approaches -2 from the right is infinity. So there is no limit. We say that that is unbounded. And if we flip this around here and we look at the limit of f as x approaches -2 from the left side, so meaning we're approaching -2 from this direction, what is f doing? Well, here if we travel along the curve, here is the curve where the function is for values less than -2. But as we approach -2 from the left, we see that the curve goes down. So downward, negative y values, negative function values, that limit is -infinity. So here's the reciprocal function. This is another one of our 12 basic functions. Here's the graph of the reciprocal function. The reciprocal function is f of x equals 1 over x. That's a parent function. So here's the graph of 1 over x. The domain of 1 over x is -infinity to 0, union 0 to +infinity. The range is negative infinity to 0, union 0 to positive infinity. Continuity of this function is continuous everywhere except x equals 0. Remember, a test for continuity, if we take our pencil and trace the curve, and here we would have to pick up our pencil and put it back down up here to continue tracing this curve. So we have a discontinuity at x equals 0. So it's continuous everywhere except at x equals 0. The decreasing or increasing nature of the function is decreasing on the interval negative infinity to 0. So what's happening to the function values on that interval, negative infinity to 0? Well, here we go. The function is decreasing. If we resume up here, as we increase x, the function is decreasing again. So this function is decreasing on two different intervals. The function has some symmetry. It's symmetric with respect to the origin because it's an odd function. We say that it is unbounded. Okay, its function values have no bound. There are no local extrema. There is a horizontal asymptote at y equals 0. Okay, so the x-axis basically is what that, another way to say that. That's a horizontal asymptote. And then there is a vertical asymptote at x equals 0. It's in behavior. The limit as x approaches negative infinity of f, so meaning as x goes this direction, this graph gets closer and closer to the x-axis, never hits the x-axis, so its limit would be 0. And the same thing, as x increases without bound, then what happens to the graph? Well, the curve gets closer and closer to the x-axis on this side, from the positive side. But those two limits are equal. Okay? Those two limits are equal. So we can talk about transforming the reciprocal function or the parent function to get other functions. So describe how the graph of the function can be obtained by transforming the graph of f of x equals 1 over x. Identify the horizontal and vertical asymptotes and use limits to describe the corresponding behavior, and then sketch the graph of the function. So we take our parent function f of x, and we want to determine how would we get the function g of x, which is negative 2 over x. How would we get function h of x, which is negative 2 over the quantity x plus 3. And how could we get k of x, which is 2x plus 4 over the quantity x plus 3. So the graph of f is shown here. So there's our reciprocal function. So let's start with g. G of x is negative 2 over x, which is the same, if you think about it, the equivalent of negative 2 times f of x, because what is f of x? F of x is 1 over x. So negative 2 times 1 over x is negative 2 over x. So that's how we get g. So g is formed by multiplying f by negative 2. So since we're multiplying it by a negative value, we're going to reflect f across the x-axis. And the 2 is going to tell us that we're going to stretch vertically by a factor of 2. So that would generate this graph. So again, if you go back and compare these two graphs, there's a reflection across the x-axis and there is some vertical stretching. There's a vertical asymptote at x equals 0 still. There's still a horizontal asymptote at y equals 0, so those did not change because the function is not defined at x equals 0. That gives us our vertical asymptote. And then here's the limit nature of the function. Part B, we talk about the function h of x. H of x is the function negative 2 over the quantity x plus 3. Well, if you think about it, g of x was 2 over x, negative 2 over x. So if we take out the x and put in x plus 3, we basically have the function g evaluated at x plus 3. Well, g was 2 times, negative 2 times f. So these graphs are all related to each other. We can trace it back to the parent function. So again, we're reflecting across the x-axis. We're stretching vertically by a factor of 2. This time we're translating 3 units left. Because we're adding 3 to x, we're going to translate everything to the left 3 units. So we have a vertical asymptote now at x equals negative 3. Originally it was right here on the y-axis. So that gets translated 3 units to the left. Our horizontal asymptote is still at y equals 0. And here is our limiting behavior of this function. As x goes to negative and positive infinity, the limit is 0. As x approaches negative 3 from the right, the function values approach negative infinity. Okay, that's approaching negative 3 from the right. The graph is going downward. And as we approach negative 3 from the left, so here, the graph is going upward. Positive infinity is that limit. C, which is k of x, is again, you can see how k is developed from f. We can trace it back to f. Negative 2 times f at x plus 3, add 2 to it. So we're still reflecting f across the x-axis. We're still stretching vertically by a factor of 2. We're translating 3 units left, but now we're also going to translate 2 units up. So the vertical asymptote is here. Now the horizontal asymptote was the x-axis. Now it is 2 because we've translated everything upward, so the asymptote gets translated 2 units upward as well. And here is our limiting behavior. What happens to the function as x goes to infinity and negative infinity equals 2. What happens as our x values approach negative 3 from the left and the right? Still, as we approach from the right, negative infinity, because the graph goes this direction, and as we approach negative 3 from the left, the graph is going upward, so that is a positive infinity limit. So here's some generalities for the graph of a rational function. So the graph of y equals f of x over g of x equals, here is f, okay, in general, and here is g in general. So if you go by the notation, the power of f, we're going to refer to that as n, and the power of g, we're going to refer that as m here in behavior. So here's our first situation, our first possibility. If n is less than m, the end behavior asymptote is the horizontal asymptote y equals 0. So what that means is that if the power of the numerator is less than the power of the denominator, then we're going to have a horizontal asymptote of y equals 0. Okay? And if you think about that, if the power of, so we have, just look at x to the n over x to the m. If n is less than m, then that means that x to the m dominates this function. As x increases, the denominator is going to be increasing much faster than the numerator. So overall, the value of that function is going to be getting smaller and smaller, which means its approaching, or its limit of its value is 0. That's where the horizontal asymptote y equals 0 comes from, because the limiting value of that function as x increases to infinity is 0. Now if n equals m, the end behavior asymptote is the horizontal asymptote y equals a sub n over b sub m. Okay? So let me write this out. If I have a sub n times x to the n over b sub m times x to the m, and n equals m, that means the power of the numerator and the power of the denominator are the same, then that means that as x increases, as x goes to infinity, the overall value of the numerator and the overall value of the denominator are going to be the same in terms of x, but really the value of that is going to be these coefficients, the ratio of these coefficients. These two values here are essentially the same. So what's left, I guess you could say, is a sub n over b sub m. So the coefficients on the leading terms of the numerator over the denominator's leading coefficient is going to be the value of that horizontal asymptote if the power of the numerator is the same as the power of the denominator. Okay, so the third case here is if n is greater than m, then the end behavior asymptote is the quotient polynomial function, y equals q of x, where f of x equals g of x times q of x plus r of x. There is no horizontal asymptote. So what that means is we're talking about a slant asymptote, or it could also be called an oblique asymptote. Okay? So if the numerator dominates the overall function, then we're going to have some type of a slant or oblique asymptote. So the graph of y equals f of x over g of x, again, has the following characteristics. Vertical asymptotes, these occur at the zeros of the denominator, provided that the zeros are not also zeros of the numerator of equal or greater multiplicity. X-intercepts, these are going to occur at the zeros of the numerator, which are not also zeros of the denominator. And y-intercepts, this is the value of f at 0, if it's defined. So find the asymptotes of the function f of x equals 2 times the quantity x plus 3 times the quantity x minus 3 all over the quantity x plus 1 times the quantity x plus 5. What are all the asymptotes of that function? So go ahead and pause the video, and when you're ready, play it and we'll look at the solution. So there are vertical asymptotes at the zeros of the denominator, x equals -1 and x equals -5. The end behavior asymptote is at y equals 2. And it may not be obvious why that is, but if you look at your factors of f in the numerator, if you were to multiply this out, you would have a quadratic in the numerator and you would also have a quadratic in the denominator. So we're going to have an x squared over an x squared. When that's the case, we would have 2x squared over 1x squared, so that's where y equals 2 comes from. It's the coefficients on these two, the ratio of those coefficients. Find the asymptotes and intercepts of f and graph f. So go ahead and pause the video, determine these asymptotes and intercepts, and take a crack at sketching this by hand. So the numerator is 0 when x equals 1, so the x-intercept is 1. The value of the function at 0 is 1/6, so the y-intercept is 1/6. The denominator is 0 when x equals 2 and x equals -3. Vertical asymptotes at x equals 2 and x equals -3 are generated by those zeros. The degree of the numerator is less than the degree of the denominator, so we have a horizontal asymptote at y equals 0. And this is what the graph of f looks like. You can see we have a piece here, we have a piece here, and then we have another piece here. So it's kind of interesting. 2 vertical asymptotes. This would be difficult to sketch by hand. But if we were to do it, we would just have to think about what the behavior is going to look like in terms of remembering what the reciprocal function looks like, and then trying to develop off of that reciprocal function what this graph looks like. You're not going to have to be able to do those by hand right now. So if we wanted to look at a graph of that function, we would just do it on our calculator. All right? So if you had any questions about the examples that we did or any of the content in the video, please be prepared to ask those questions in class.